All right, let's get started.
Good take, good take.
Oh, jeez.
And cut. Okay, you guys ready?
Yeah.
Everybody thinks we make GPUs. But NVIDIA is so much more than that. This whole keynote is going to be about that.
Okay, so we'll start at the top.
Examples of the use cases and then seeing it in action. That's kind of the flow.
It's such a compelling story.
I'm super nervous about this.
Just gotta get in the rhythm.
We're 2 weeks away from it. You guys can go really, really make it great.
We should take a swing at it.
Yeah, that's the plan. I think we need to get daily status on that animation.
Can you mute? Because I hear myself.
Sorry.
What's the drop date for all the videos?
It needs to be done on the 28th.
Did you get all that?
Safe travels, everybody.
Super excited to see everyone.
See you guys soon. Okay.
Bye.
We're basically moving as fast as the world can absorb technology. So we've got to leapfrog ourselves. Isn't it right? Now the spine, you just have to figure out a way to make it pop. You know what I'm saying? You know what I'm saying? You want to... Yeah, that kind of thing. Thank you. I'm super late. Let's go.
欢迎 Nvidia 创办人暨执行长黄仁勋先生。
Please welcome to the stage Nvidia founder and CEO, Jensen Huang.
I am very happy to be back. Thank you, NTU, for letting us use your stadium. The last time I was here, I received a degree from NTU. And I gave the run, don't walk speech. And today we have a lot to cover. So I cannot walk, I must run. We have a lot to cover. I have many things to tell you. I'm very happy to be here in Taiwan. Taiwan is the home of our treasured partners. This is, in fact, where everything NVIDIA does begins. Our partners and ourselves take it to the world. Taiwan and our partnership has created the world's AI infrastructure. Today, I want to talk to you about several things. One, what is happening and the meaning of the work that we do together? What is generative AI? What is its impact on our industry and on every industry? A blueprint for how we will go forward and engage this incredible opportunity. And what's coming next? Generative AI and its impact, our blueprint, and what comes next. These are really, really exciting times. A restart of our computer industry, an industry that you have forged, an industry that you have created, and now you're prepared for the next major journey. But before we start, NVIDIA lives at the intersection of computer graphics, simulations, and artificial intelligence. This is our soul. Everything that I show you today is simulation. It's math, it's science, it's computer science, it's amazing computer architecture. None of it's animated, and it's all homemade. This is NVIDIA Soul, and we put it all into this virtual world we call Omniverse. Please enjoy. I want to speak to you in Chinese, but I have so much to tell you, I have to think too hard to speak Chinese. So I have to speak to you in English. At the foundation of everything that you saw was two fundamental technologies: accelerated computing and artificial intelligence running inside the Omniverse. Those two technologies, those two fundamental forces of computing are going to reshape the computer industry. The computer industry is now some 60 years old. In a lot of ways, everything that we do today was invented the year after my birth, in 1964. The IBM System 360 introduced central processing units, general purpose computing, the separation of hardware and software through an operating system, multitasking, I/O subsystems, DMA, all kinds of technologies that we use today, architectural compatibility, backwards compatibility, family compatibility, all of the things that we know today about computing largely described in 1964. Of course, the PC revolution democratized computing and put it in the hands and the houses of everybody. And then in 2007, the iPhone introduced mobile computing and put the computer in our pocket. Ever since, everything is connected and running all the time through the mobile cloud. This last 60 years, we saw several, just several, not that many actually, 2 or 3 major technology shifts. 2 or 3 tectonic shifts in computing, where everything changed. And we're about to see that happen again. there are two fundamental things that are happening. The first is that the processor, the engine by which the computer industry runs on, the central processing unit, the performance scaling has slowed tremendously. And yet, the amount of computation we have to do is still doubling very quickly, exponentially. If processing requirement, if the data that we need to process continues to scale exponentially, but performance does not, we will experience computation inflation. And in fact, we're seeing that right now as we speak. The amount of data center power that's used all over the world is growing quite substantially. The cost of computing is growing. We are seeing computation inflation. This, of course, cannot continue. The data is going to continue to increase exponentially, and CPU performance scaling will never return. There is a better way. For almost 2 decades now, we've been working on accelerated computing. CUDA augments a CPU, offloads and accelerates the work that a specialized processor can do much, much better. In fact, the performance is so extraordinary that it is very clear now, as CPU scaling has slowed and eventually substantially stopped, we should accelerate everything. I predict that every application that is processing intensive will be accelerated, and surely every data center will be accelerated in the near future. Now, accelerated computing is very sensible. It's very common sense. If you take a look at an application, and here the 100T means 100 units of time. It could be 100 seconds, it could be 100 hours, and in many cases, as you know, we're now working on artificial intelligence applications that run for 100 days. The 1T is code that requires sequential processing, where single-threaded CPUs are really quite essential. Operating systems, control logic, really essential to have one instruction executed after another instruction. However, there are many algorithms, computer graphics is one, that you can operate completely in parallel. Computer graphics, image processing, physics simulations, combinatorial optimizations, graph processing, database processing, and of course, the very famous linear algebra of deep learning. There are many types of algorithms that are very conducive to acceleration through parallel processing. So we invented an architecture to do that. By adding the GPU to the CPU, the specialized processor can take something that takes a great deal of time and accelerate it down to something that is incredibly fast. And because the two processors can work side by side, they're both autonomous and they're both separate, independent that is, we could accelerate what used to take 100 units of time down to 1 unit of time. Well, the speed up is incredible. It almost sounds unbelievable. It almost sounds unbelievable. But today I'll demonstrate many examples for you. The benefit is quite extraordinary. 100 times speed up, but you only increase the power by about a factor of 3. And you increase the cost by only about 50%. We do this all the time in the PC industry. We add a GPU, a $500 GPU, GeForce GPU, to a $1,000 PC, and the performance increases tremendously. We do this in a data center. A $1 billion data center, we add $500 million worth of GPUs, and all of a sudden, it becomes an AI factory. This is happening all over the world today. Well, the savings are quite extraordinary. You're getting 60 times performance per dollar. 100 times speed up, you only increase your power by 3x. 100 times speed up, you only increase your cost by 1.5x. The savings are incredible. The savings are measured in dollars. It is very clear that many, many companies spend hundreds of millions of dollars processing data in the cloud. If it was accelerated, it is not unexpected that you could save hundreds of millions of dollars. Now, why is that? Well, the reason for that is very clear. We've been experiencing inflation for so long in general purpose computing. Now that we finally determined to accelerate, there's an enormous amount of captured loss that we can now regain. A great deal of captured, retained waste that we can now relieve out of the system, and that will translate into savings. Savings in money, savings in energy. And that's the reason why you've heard me say, the more you buy, the more you save. And now I've shown you the mathematics. It is not accurate, but it is correct. Okay, that's called CEO math. CEO math is not accurate, but it is correct. The more you buy, the more you save. Well, accelerated computing does deliver extraordinary results, but it is not easy. Why is it that it saves so much money, but people haven't done it for so long? The reason for that is because it's incredibly hard. There is no such thing as a software that you can just run through a C compiler and all of a sudden that application runs 100 times faster. That is not even logical. If it was possible to do that, they would have just changed the CPU to do that. You, in fact, have to rewrite the software. That's the hard part. The software has to be completely rewritten so that you could refactor, re-express the algorithms that was written on a CPU so that it could be accelerated, offloaded, accelerated, and run in parallel. That computer science exercise is insanely hard. Well, we've made it easy for the world over the last 20 years. Of course, the very famous Cudaga, the deep learning library that processes neural networks. We have a library for AI physics that you could use for fluid dynamics and many other applications where the neural network has to obey the laws of physics. We have a great new library called Ariel that is a CUDA accelerated 5G radio so that we can software define and accelerate the telecommunications networks the way that we've software defined the world's networking internet. And so the ability for us to accelerate that allows us to turn all of telecom into essentially the same type of platform, a computing platform, just like we have in the cloud. cuLitho is a computational lithography platform that allows us to process the most computationally intensive parts of chip manufacturing, making the mask. TSMC is in the process of going to production with cuLitho, saving enormous amounts of energy and enormous amounts of money, but the goal for TSMC is to accelerate their stack so that they're prepared for even further advances in algorithm and more computation for deeper and deeper, narrow and narrow transistors. Parabricks is our gene sequencing library. It is the highest throughput library in the world for gene sequencing. cuOpt is an incredible library for combinatorial optimization, route planning optimization, the traveling salesman problem, incredibly complicated. Scientists have largely concluded that you needed a quantum computer to do that. We created an algorithm that runs on accelerated computing that runs lightning fast. 23 world records. We hold every single major world record today. cuQuantum is an emulation system for a quantum computer. If you want to design a quantum computer, you need a simulator to do so. If you want to design quantum algorithms, you need a quantum emulator to do so. How would you do that? How would you design these quantum computers, create these quantum algorithms, if the quantum computer doesn't exist? Well, you use the fastest computer in the world that exists today. And we call it, of course, NVIDIA CUDA. And on that, we have an emulator that simulates quantum computers. It is used by several 100,000 researchers around the world. It is integrated into all the leading frameworks for quantum computing, and is used in scientific supercomputing centers all over the world. cuDF is an unbelievable library for data processing. Data processing consumes the vast majority of cloud spend today. All of it should be accelerated. Cuda accelerates the major libraries used in the world. Spark, many of you probably use Spark in your companies. Pandas, a new one called Polar, and of course, NetworkX, which is a graph processing database library. And so these are just some examples. There are so many more. Each one of them had to be created so that we could enable the ecosystem to take advantage of accelerated computing. If we hadn't created Cuda alone wouldn't have been possible for all of the deep learning scientists around the world to use. Because Cuda and the algorithms that are used in TensorFlow and PyTorch, the deep learning algorithms, the separation is too far apart. It's almost like trying to do computer graphics without OpenGL. It's almost like doing data processing without SQL. These domain-specific libraries are really the treasure of our company. We have 350 of them. These libraries is what it takes and what has made it possible for us to have such open so many markets. I'll show you some other examples today. Well, just last week, Google announced that they put Cuda in the cloud and accelerate Pandas. Pandas is the most popular data science library in the world. Many of you in here probably already use Pandas. It's used by 10 million data scientists in the world. Downloaded 170 million times each month. It is the Excel, it is the spreadsheet of data scientists. Well, with just one click, you can now use Pandas in Colab, which is Google's cloud data centers platform, accelerated by Cuda. The speed up is really incredible. Let's take a look. That was a great demo, right? Didn't take long. When you accelerate data processing that fast, demos don't take long. Okay, well, Cuda has now achieved what people call a tipping point, but it's even better than that. Cuda has now achieved a virtuous cycle. This rarely happens. If you look at history and all the computing architectures, computing platforms, in the case of microprocessors, CPUs, it has been here for 60 years. It has not been changed for 60 years. At this level, this way of doing computing, accelerated computing, has been around, creating a new platform is extremely hard because it's a chicken and egg problem. If there are no developers that use your platform, then of course there will be no users. But if there are no users, there are no install base. If there are no install base, developers aren't interested in it. Developers want to write software for a large install base. But a large install base requires a lot of applications so that users would create that install base. This chicken or the egg problem has rarely been broken. And it's taken us now 20 years, one domain library after another, one acceleration library another, and now we have 5 million developers around the world. We serve every single industry, from healthcare, financial services, of course the computer industry, automotive industry, just about every major industry in the world, just about every field of science. Because there are so many customers for our architecture, OEMs and cloud service providers are interested in building our systems. System makers, amazing system makers like the ones here in Taiwan are interested in building our systems, which then takes and offers more systems to the market, which of course creates greater opportunity for us, which allows us to increase our scale, R&D scale, which speeds up the application even more. Well, every single time we speed up the application, the cost of computing goes down. This is that slide I was showing you earlier. 100x speed up translates to 97, 96%, 98% savings. And so when we go from 100x speed up to 200x speed up to 1000x speed up, the savings, the marginal cost of computing continues to fall. Well, of course, we believe that by reducing the cost of computing incredibly, the market, developers, scientists, inventors will continue to discover new algorithms that consume more and more and more computing, so that one day something happens, that a phase shift happens, that the marginal cost of computing is so low that a new way of using computers emerge. In fact, that's what we're seeing now. Over the years, we have driven down the marginal cost of computing in the last 10 years in one particular algorithm by 1 million times. Well, as a result, it is now very logical and very common sense to train large language models with all of the data on the internet. Nobody thinks twice. This idea that you could create a computer that could process so much data to write its own software, the emergence of artificial intelligence was made possible because of this complete belief that if we made computing cheaper and cheaper and cheaper, somebody's going to find a great use. Well, today, CUDA has achieved the virtuous cycle. Install base is growing. Computing cost is coming down, which causes more developers to come up with more ideas, which drives more demand. And now we're in the beginning of something very, very important. But before I show you that, I want to show you what is not possible if not for the fact that we created CUDA, that we created the modern version of the modern big bang of AI, generative AI. What I'm about to show you would not be possible. This is Earth 2. The idea that we would create a digital twin of the Earth, that we would go and simulate the Earth so that we could predict the future of our planet to better avert disasters or better understand the impact of climate change so that we can adapt better, so that we could change our habits now. This digital twin of Earth is probably one of the most ambitious projects that the world's ever undertaken, and we're taking large steps every single year, and I'll show you results every single year, but this year we made some great breakthroughs. Let's take a look.
On Monday, the storm will veer north again and approach Taiwan. There are big uncertainties regarding its path. Different paths will have different levels of impact on Taiwan.
想象一个我们能够预测未来的世界，数位孪生反映真实情况的虚拟世界，让我们看见未来。数位孪生是一种反映真实世界的虚拟模型，让我们能够从今天的行为来预测对未来世界的影响。介绍一下 Nvidia Earth 2， 一个利用 AI、物理模拟和电脑图形技术来预测全球气候的数位孪生。Cudaga 是 Nvidia 的生成式 AI 模型，它在 WRF 数值模拟的基础上训练而成，能够以12倍更高的解析度生成天气模式，从25公里提高到2公里，这代表了区域天气预测的一个巨大飞跃。令人惊讶的是 ，Cudaga AI 比传统的物理模拟方法快1000倍，且能源效率高3000倍。在台湾的中央气象局是用这些模型来更精确地预测台风登陆点。但我们并不止步于此，下一个前沿是超本地预测，能精确到数十米，并考虑到城市基础设施的影响。Cudaga AI 还在使用像是 Palm 生成的高解析度数据进行训练，一个极高解析度的物理模型，用于模拟大气和海洋边界层。当与天气模拟风场结合一起时，它可以模拟建筑物周围的气流。单极强风汇聚的情况，我们预计能够预测像下冲这样的现象。当强风汇聚到街道层，会有可能造成损坏并影响行人。Nvidia Earth 2是一个绝佳范例，它融合了人工智慧、物理模拟 和观测数据，可以帮助国家和公司预见未来，并应对极端天气的影响。
Someday, in the near future, we will have continuous weather prediction at every square kilometer on the planet. You will always know what the climate's going to be. You will always know. And this will run continuously because we've trained the AI, and the AI requires so little energy. And so this is just an incredible achievement. I hope you enjoyed it. And very importantly, 我的国语讲的标准吗？ The truth is, that was a Jensen AI. That was not me. I wrote it, but an AI, Jensen AI, had to say it. 我的国语不够好。 Because of our dedication to continuously improve the performance of drive the cost down, AI researchers discovered Cuda in 2012. That was Nvidia's first contact with AI. This was a very important day. We had the good wisdom to work with the scientists to make it possible for deep learning to happen. And AlexNet achieved, of course, a tremendous computer vision breakthrough. But the great wisdom was to take a step back and understanding what was the background, what is the foundation of deep learning? What is its long-term impact? What is its potential? And we realized that this technology has great potential to scale. An algorithm that was invented and discovered decades ago, all of a sudden, because of more data, larger networks, and very importantly, a lot more compute, all of a sudden, deep learning was able to achieve what no human algorithm was able to. Now imagine if we were to scale up the architecture even more, larger networks, more data, and more compute, what could be possible? So we dedicated ourselves to reinvent everything. After 2012, we changed the architecture of our GPU to add tensor cores. We invented NVLink. That was 10 years ago now. Cudaga, TensorRT, Nickel. We bought Mellanox, TensorRT LM, the Triton inference server. And all of it came together on a brand new computer nobody understood. Nobody asked for it. Nobody understood it. And in fact, I was certain nobody wanted to buy it. And so we announced it at GTC, and OpenAI, a small company in San Francisco, saw it. And they asked me to deliver one to them. I delivered the first DGX, the world's first AI supercomputer, to OpenAI in 2016. Well, after that, we continued to scale. From one AI supercomputer, one AI appliance, we scaled it up to large supercomputers, even larger. By 2017, the world discovered transformers so that we could train enormous amounts of data and recognize and learn patterns that are sequential over large spans of time. It is now possible for us to train these large language models to understand and achieve a breakthrough in natural language understanding. And we kept going after that. We built even larger ones. And then in November 2022, trained on thousands, tens of thousands of NVIDIA GPUs in a very large AI supercomputer, OpenAI announced ChatGPT. 1 million users after 5 days. 1 million after 5 days, 100 million after 2 months. The fastest growing application in history. And the reason for that is very simple. It is just so easy to use, and it was so magical to use. To be able to interact with a computer like it's human. Instead of being clear about what you want, it's like the computer understands your meaning. It understands your intention. Oh, I think here it asked the closest night market. As you know, the night market is very important to me. So when I was young, I think I was 4.5 years old. I used to love going to the night market because I just love watching people. And so we went, my parents used to take us to the night market. 圆环, 讲对吗? 圆环, 去吃蚵仔煎. And I love going. And one day, my face, you guys might see that I have a large scar on my face. My face was cut because somebody was washing their knife, and I was a little kid. But my memories of the night market is so deep because of that. And I used to love, I still love going to the night market. And I just need to tell you guys this. The Tonghua night market is really good because there's a lady, she's been working there for 43 years. She's the fruit lady, and it's in the middle of the middle between the two. Go find her, okay? She, 做赞的，这喝价。She's really terrific. I think it would be funny after this, all of you go to see her. Every year she's doing better and better. Her car test has improved, and yeah, I just love watching her succeed. Anyways, ChatGPT came along, and something is very important in this slide. Here, let me show you something. This slide, okay, and this slide. The fundamental difference is this. Until ChatGPT revealed it to the world, AI was all about perception, natural language understanding, computer vision, speech recognition. It's all about perception and detection. This was the first time the world saw a generative AI. It produced tokens, one token at a time. And those tokens were words. Some of the tokens, of course, could now be images or charts or tables, songs, words, speech, videos. Those tokens could be anything. Anything that you could learn the meaning of. It could be tokens of chemicals, tokens of proteins, genes. You saw earlier in Earth 2, we were generating tokens of the weather. We can learn physics. If you can learn physics, you could teach an AI model physics. The AI model could learn the meaning of physics, and it can generate physics. We were scaling down to 1 kilometer, not by using filtering, it was generating. And so we can use this method to generate tokens for almost anything of value. We can generate steering wheel control for a car. We can generate articulation for a robotic arm. Everything that we can learn, we can now generate. We have now arrived not at the AI era, but a generative AI era. But what's really important is this. This computer that started out as a supercomputer has now evolved into a data center, and it produces one thing. It produces tokens. It's an AI factory. This AI factory is generating, creating, producing something of great value, a new commodity. In the late 1890s, Nikola Tesla invented an AC generator. We invented an AI generator. The AC generator generated electrons. Nvidia's AI generator generates tokens. Both of these things have large market opportunities. It's completely fungible in almost every industry. And that's why it's a new industrial revolution. We have now a new factory producing a new commodity for every industry that is of extraordinary value. And the methodology for doing this is quite scalable. And the methodology of doing this is quite repeatable. Notice how quickly so many different AI models, generative AI models, are being invented, literally daily. Every single industry is now piling on. For the very first time, the IT industry, which is $3 trillion, $3 trillion IT industry, is about to create something that can directly serve $100 trillion of industry. No longer just an instrument for information storage or data processing, but a factory for generating intelligence for every industry. This is going to be a manufacturing industry, not a manufacturing industry of computers, but using the computers in manufacturing. This has never happened before. Quite an extraordinary thing. What started with accelerated computing, led to AI, led to generative AI, and now an industrial revolution. Now the impact to our industry is also quite significant. Of course, we could create a new commodity, a new product we call tokens for many industries, but the impact to ours is also quite profound. For the very first time, as I was saying earlier, in 60 years, every single layer of computing has been changed. From CPUs, general purpose computing, to accelerated GPU computing, where the computer needs instructions, now computers process LLMs, large language models, AI models. And whereas the computing model of the past is retrieval-based, almost every time you touch your phone, some pre-recorded text or pre-recorded image or pre-recorded video is retrieved for you and recomposed based on a recommender system to present it to you based on your habits. But in the future, your computer will generate as much as possible, retrieve only what's necessary. And the reason for that is because generated data requires less energy to go fetch information. Generated data also is more contextually relevant. It will encode knowledge, it will encode your understanding of you, and instead of get that information for me or get that file for me, you just say, ask me for an answer. And instead of a tool, instead of your computer being a tool that we use, the computer will now generate skills. It performs tasks. And instead of an industry that is producing software, which was a revolutionary idea in the early 90s. Remember, the idea that Microsoft created for packaging software revolutionized the PC industry. Without packaged software, what would we use the PC to do? It drove this industry. And now we have a new factory, a new computer. And what we will run on top of this is a new type of software. And we call it NIMS, NVIDIA Inference Microservices. Now what happens is the NIM runs inside this factory. And this NIM is a pre-trained model. It's an AI. Well, this AI is, of course, quite complex in itself. But the computing stack that runs AIs are insanely complex. When you go and use ChatGPT, underneath their stack is a whole bunch of software. Underneath that prompt is a ton of software. And it's incredibly complex because the models are large, billions to trillions of parameters. It doesn't run on just one computer, it runs on multiple computers. It has to distribute the workload across multiple GPUs, tensor parallelism, pipeline parallelism, data parallelism, all kinds of parallelism, expert parallelism, all kinds of parallelism. distributing the workload across multiple GPUs, processing it as fast as possible, because if you are in a factory, if you run a factory, your throughput directly correlates to your revenues. Your throughput directly correlates to quality of service, and your throughput directly correlates to the number of people who can use your service. We are now in a world where data center throughput, utilization is vitally important. It was important in the past, but not vitally important. It was important in the past, but people don't measure it. Today, every parameter is measured. Start time, uptime, utilization, throughput, idle time, you name it. Because it's a factory. When something is a factory, its operations directly correlate to the financial performance of the company. And so we realized that this is incredibly complex for most companies to do. So what we did was we created this AI in a box, and it contains an incredible amount of software. Inside this container is CUDA, cuDNN, TensorRT, Triton for inference services. It is cloud native so that you could auto scale in a Kubernetes environment. It has management services and hooks so that you can monitor your AIs. It has common APIs, standard APIs, so that you could literally chat with this box. You download this NIM and you can talk to it. So long as you have CUDA on your computer, which is now, of course, everywhere. It's in every cloud, available from every computer maker. It is available in hundreds of millions of PCs. When you download this, you have an AI, and you can chat with it like ChatGPT. All of the software is now integrated. 400 dependencies, all integrated into one. We tested this NIM, each one of these pre-trained models, against our entire install base that's in the cloud, all the different versions of Pascal and Amperes and Hoppers and all kinds of different versions. I even forget some. NIMS, incredible invention. This is one of my favorites. And of course, as you know, we now have the ability to create large language models and pre-trained models of all kinds. And we have all of these various versions, whether it's language-based or vision-based or imaging-based, or we have versions that are available for healthcare, digital biology. We have versions that are digital humans that I'll talk to you about. And the way you use this, just come to ai.nvidia.com. And today we just posted up in Hugging Face the Llama 3 NIM, fully optimized. It's available there for you to try. And you can even take it with you. It's available to you for free. And so you could run it in the cloud, run it in any cloud. You could download this container, put it into your own data center, and you could host it, make it available for your customers. We have, as I mentioned, all kinds of different domains. Physics, some of it is for semantic retrieval called RAGs, vision languages, all kinds of different languages. And the way that you use it is connecting these microservices into large applications. One of the most important applications in the coming future, of course, is customer service agents. Customer service agents are necessary in just about every single industry. It represents trillions of dollars of customer service around the world. Nurses are customer service agents in some ways. Some of them are non-prescription or non-diagnostics based nurses are essentially customer service. Customer service for retail, for quick service foods, financial services, insurance, just tens and tens of millions of customer service can now be augmented by language models and augmented by AI. And so these boxes that you see are basically NIMs. Some of the NIMs are reasoning agents. Given a task, figure out what the mission is, break it down into a plan. Some of the NIMs retrieve information. Some of the NIMs might go and do search. Some of the NIMs might use a tool like cuOpt that I was talking about earlier. It could use a tool that could be running on SAP. And so it has to learn a particular language called ABAP. Maybe some NIMs have to do SQL queries. And so all of these NIMs are experts that are now assembled as a team. So what's happening? The application layer has been changed. What used to be applications written with instructions are now applications that are assembling teams of AIs. Very few people know how to write programs. Almost everybody knows how to break down a problem and assemble teams. Every company, I believe, in the future will have a large collection of NIMs, and you would bring down the experts that you want. You connect them into a team, and you don't even have to figure out exactly how to connect them. You just give the mission to an agent, to a NIM, to figure out who to break the tasks down and who to give it to. And that central, the leader of the application, if you will, the leader of the team, would break down the task and give it to the various team members. The team members would perform their task, bring it back to the team leader. The team leader would reason about that and present an information back to you. Just like humans. This is in our near future. This is the way applications are going to look. Now, of course, we could interact with these AI services with text prompts and speech prompts. However, there are many applications where we would like to interact with what is otherwise a human-like form. We call them digital humans. NVIDIA has been working on digital human technology for some time. Let me show it to you. And before I do that, hang on a second. Before I do that, okay, digital humans has the potential of being a great interactive agent with you. They make much more engaging. They could be much more empathetic. And of course, we have to cross this incredible chasm, this uncanny chasm of realism, so that the digital humans would appear much more natural. This is, of course, our vision. This is a vision of where we love to go, but let me show you where we are.